Thank you for this introduction. So good afternoon. I will present our current work on the simulation of hydrogen embrittlement. So before, which one is it? Okay. So before starting, some background to this work. So in France, we have something like 400,000 kilometers of pipelines made of vintage and modern steel. And there's the possibility to use these pipelines to transport hydrogen or blends of hydrogen and methane. As we know, ferritic steel are highly susceptible to hydrogen embrittlement. So there is a lot of experimental work needed to characterize its effect. But also, I strongly believe that it's important to develop models to help interpreting these tests and to check that the experimental database is consistent. Okay, so I will describe the proposed model, give you some hints about the finite element application, and try to go through three examples and conclude. Okay, so which ingredient do we want to have in our simulation? Obviously, we're not interested in very embrittled material. These materials, they must keep some ductility. So we must have elastoplasticity, but also finite strain, a lot of deformation before failure. We are interested in failure, so we need to incorporate damage. And since we want to stay in the more or less ductile regime, we use a model which is based on the Gerson-Twerger-Needleman model. There is this other possibility, if the material is quite brittle, to use phase field modeling. And indeed, we need to model hydrogen diffusion within the material, and we need to couple these three phenomena. So we are using the finite element method. We use a strongly coupled methodology, so we solve for mechanics and diffusion at the same time. Everything is implemented in our code, which is co-developed with ONERA, the French aerospace lab. And we need to implement indeed constitutive equation, but also finite elements which are adapted to this formulation. So here are some equations, which I'm going to describe rapidly. You probably know all of them. So we base our modeling of the early work of Sofronis McMeeking, where we have the lattice hydrogen and trapped hydrogen, with the possibility of having multiple traps. The important thing here, because it's coupling, I think that is red, it indicates a coupling with mechanics. So here, that's the flux of hydrogen, which is related to the gradient of the lattice hydrogen, but also there is a term which is proportional to the gradient of pressure, and it's very important because at a crack tip, pressure is very high, and hydrogen will diffuse toward crack tips and cause local embrittlement. What is important for traps is the trap density, N here. There's also a coupling term because one of the possible traps are dislocation. And if you have plastic deformation, then you increase the density of dislocation and you will increase the trap density. So here's another coupling term. Right now, we are using the Oriani equilibrium, instantaneous equilibrium, which introduces this binding energy, which is very, very important. There is also the possibility to use the Foster-McNabb, which introduced some kinetics. Some more possible coupling, the flow stress may be affected by the hydrogen content. We have seen some examples just before, but it seems to be increasing in some cases. In some cases also it's decreasing, so it's a bit confusing for me. And we need boundary conditions, so we are using either Dirichlet boundary condition, prescribing the lattice concentration, or Neumann boundary condition where the flux is zero. We need ductile damage, so I'm probably not very familiar with this kind of modeling. So that's a model where we introduce damage, and damage in ductile material corresponds to void growth, but also void nucleation, the creation of new voids. And that's what this formula here is more or less representing. The Q1 and Q2 terms are related to growth, and growth may be affected by the hydrogen concentration. But also, There's the possibility that nucleation can be affected by hydrogen. In this steel, there's a secondary nucleation mechanism, which is the debonding of carbides from the matrix. And we can imagine that when you have more hydrogen, debonding becomes easier. But if you are thinking of a specific mechanism, such as hydrogen-enhanced decohesion, then we add another term, which is driven by the plastic strain, but also by the magnitude of the principal stress. So if the principal stress is very high, then it will break faster. And that's the idea here, that the critical stress is a function of the hydrogen concentration. If it's close to zero, there's no effect, so it should go to infinity, more or less. If you increase the hydrogen concentration, and this red curve is, imagine the load level you have. If you have a sufficiently high concentration of hydrogen, then the material will start to fail. And we are trying different forms of these equations to match our experimental results. Most of the other hydrogen-related parameters are taken from the literature, and that's something I don't like, but that's something we have to do. I must point out that such models are also developed in Norway on at Ghent University. Okay. Now a few hints about the implementation. There are several numerical issues when you do that. First of all, and it's not related to hydrogen, we have a constitutive equation that leads to failure. That means that the material is softening. And if you do that and use the displacement-based finite elements, then when you decrease the mesh size, you get different here load displacement curves, and there is no convergence. So there's something you must do about it. And the solution we choose here is to use non-local models, which is based on the implicit gradient theory. So we have to choose variables which are considered as non-local. The non-locality is one way to make an average around the material point in the calculation. So it does not depend on the very local value attached to one particular element. So we use the accumulated plastic strain, that's to regularize the nucleation. And we use the plastic volume variation, which is to regularize growth. To these quantities, we can attach different length scale, which basically are represented the size of the zone where we make the average, more or less. Second problem, you can have, in particular at crack tips, and that's a purely numerical issue, very large pressure variation because the pressure is poorly evaluated. So to solve the problem, you can use mixed elements with displacement, volume variation, and pressure. And you go from this checkboard pattern to this much nicer calculation of the pressure field. One nice thing is that since the pressure is known at nodes of the mesh, then the gradient can be directly computed, and we can input this gradient directly in our diffusion simulation. Okay, so obviously you shouldn't try to read that. I put this slide just to outline how many parameters we need. And that's one big problem. We need parameters for the elastoplastic behavior, so it's okay, for ductile damage, for diffusion, and for coupling. And that's a huge number of parameters. Many, some people may say too many. I don't know, you tell me. And here I show you a first example. So that's the pressurized disc test. So it's a normalized test. So you have a device where you put a disc here, that's the black part. And on one side, you pressurize either with helium or hydrogen. And what you measure is the pressure at failure. So this is the specimen of the standard, and we developed alternative specimen. And we did the test on pipeline steels, one modern and one vintage, but we got very similar results in there. So here are some experimental results. We changed the pressure rate. So the black dots here for under helium, under hydrogen are the red dots. Obviously, there is an embrittlement, but there is no rate effect, almost no rate effect. If you look at the fracture surface, on one side here, that's the hydrogen side, you see a quasi-brittle fracture and a little bit of ductile fracture on the other side. If you study this fracture surface as a function of the pressure rate, there is no effect. Which we were happy to find that because that's very consistent with these results. Okay, so we had our elastoplastic behavior, and we decided that the trapping sites were dislocation. And we use different data from the literature. Actually, we had to choose the binding energy, a high value or low value, and the number of trapping sites, low value, high value. If you take a high trap density, that's case 1 and 3, you see that you have obviously a rate effect. If you have a high rate, diffusion, hydrogen cannot diffuse in the material because it gets trapped. And this means that most of the specimen should be ductile. It's not consistent with our fractography. Here also, that's with a high binding energy, but we get the same results. We get much nicer results if the trap density is lower. And even better, that's our interpretation, when we take a relatively low 40 kilojoules per mole, a relatively low binding energy. But it's a very odd way to fit binding energy and trap density by doing mechanical tests. We should be able to measure them directly. Okay, second example. So I found this very nice paper about the hollow disk test, not hollow disk test, hollow tube test. Hollow tube test. So here you have a tube, you can pull on it, and inside is hollow, so you can put a hydrogen gas. And you pull up to failure. So if you put argon, you see that there's a lot of necking. These are tomographic images from this paper. So you get a lot of necking and shear bonds. If you are under hydrogen, you have obviously less necking, and the cracks tend to be straight. Okay? And then we were more or less able to fit the model on that. So that's the pressure, that's the force displacement curve. That's under helium, that's under argon, not nitrogen, argon, but it's the same. We can reproduce the ductility change, but also it's more important from my point of view here, we can represent what we get slant fracture when it's ductile and flat fracture under hydrogen. Okay. Last example, I pointed out that it's not a good idea to determine the diffusion parameters during mechanical tests. So we have to also work on tests which are designed for that. And I was fortunate enough to work with my colleagues at NIMS at Tsukuba to try simulating and work on the TDS test, thermal disruption spectrometry test. And we have already some papers published here. Most of the papers are 1D, and here I really try to do 3D and 2D analysis. So here, for instance, we have a simulation where you model both the permeation, so hydrogen gets into the specimen. Here it is a tape here to protect the specimen so you can apply a current. Since it's protected, hydrogen cannot get in at that place. So hydrogen goes in from the side. And then you'll see here the hydrogen concentration is going down because I also simulated the TDS cycle. And here is a TDS cycle simulation with 3 binding energies of this kind of test where we can recover the peaks. I think the real challenge here is to do the simulation of that, to do the simulation of the mechanical test using the same set of material parameter. And I think that's a very, very difficult task. So to conclude, I've rapidly showed you a model and its finite element implementation. And I'm finishing, you know. And yes, I'll give you some example. I want to point out there are a lot of numerical issues. I want to remember that I'm co-hosting this technical committee on numerical method for fracture. Our next meeting will be in Germany, in Munich, end of March next year. So if you are interested in taking part to that kind of meeting, just come to me and I will give you the info. Thank you.